Okay, today's lesson is about experimental probability and long-run frequency. The reason why we use experimental probability is generally for things that we don't know the outcome of, things that we can't find out all the possible outcomes to do the theoretical probability calculation. So examples would be things that only measured over an amount of time, so the number of cars that come down a road, the number of accidents that happen, things like that. So the key bit of information that we need to understand is to work out the experimental probability. We use this calculation, the number of times an event occurs divided by the total number of trials. Now, this will not match the theoretical probability because it's measured in a different way. But the more trials we do, it's found that the closer we get to the theoretical probability. So generally, a lot of the time, simulations are used for long-run frequency or experiments. So we're going to take a look at one with some dice. Okay, this is a simulation that's using Excel to generate the dice rolls. You can see at the moment in our experiment, the first roll was a 6, and that's why it's registered over here on our graph as a probability of 1, which is 100%. It's a bit of a no-no really to have in the graph that it's got a 1.2 because obviously that's not possible. The simulation will record the number of 1s, 2s, 3s, 4s and 5s. But what we would expect, say if we did 60 rolls, is that we would expect the frequency of these to be 10. Alright, because that's what the probability predicts. Probability predicts if the dice is fair, we should end up with 1 out of 6, and if it's 60 rolls, we would expect 10. But in reality, let's see what we get. So we've got 2 rolls there. Moving up, you can see that the probabilities should be the same, but they're not because we've had only 7 rolls. So if I then increase that to our 60 rolls, you can see that they should be 10, and we've got 11, 15, 8, 12, 8 and 6. So 60 rolls isn't really enough trials to get our answer. But if I then increase that to 600 rolls, what you can see is this balances out much more. That we end up with, if we do 600 rolls and it's 1/6, we should get 100. And what you can see is that the probabilities 105, 109, 100, 100, 105, 82, and 89. Now, some would say that it's the 5 has been unlucky. Statisticians would say that we haven't done enough trials yet. So if we change that to looking at Lotto, they used to print out all the frequencies of all the numbers. They would say that some numbers are more lucky than others. It's just that there hadn't been enough draws. The way probability works, the more trials you would get, the more it would balance out. And actually, any difference of one or another result would have little effect on their probabilities. So if we keep on increasing, and we get to 3,000 rolls. What we'd expect is a sixth of that, so 500. And you can see that the results are relatively close: 536, 521, 481, 468, 509, 485. but their probabilities with a relative frequency is very low. So for us to work out that relative frequency, all we're doing is we're going 536 divided by 3000 and so on. Now going to look at a simulation looking at coin flips. So we should know that the probability of getting head is equal to 1 out of 2, 0.5, and probability of getting a tail is equal to 0.5 as well. They're the only two outcomes. Now, what this simulation shows us is that we're going to have a table here, and if I flip a coin, we end up with a head, how many heads so far, and the probability of getting a head. So the experimental probability after one trial is 100%. So in other words, remember, that means that it's certain that when you flip a coin, you'll get a head. Obviously, one trial is not enough. So as we flip it around, we get a tail. So there's only been one head, so the probability is 1 out of 2. So therefore, we've got it. But the variation is too high at the moment that you can see with every turn, we're changing slightly. But the thing to notice in the first 10 flips is that this graph started off with large changes, but then it's starting to balance out. What we should see is that the graphs then settle down on 0.5. So this is the graph for the next 100 flips. Okay, so for the second graph, what do we notice? What we should notice is that the line is starting to level out. It's starting that the variations are becoming less and less, and it's starting to get closer to that. You can see that the next one is for 500 flips. And as we increase the number of flips that we do here, you can see that there's very little variation on the line. And that you can also see that it's pretty much bang on 0.5. And if I scroll down, you can see that the numbers are getting more and more balanced. And we can see there that the probability of getting a head in the 499th trial with 0.5. Now, what does that mean? That means that if I ran this experiment, I started off not knowing what the theoretical probability was of flipping a coin and getting a head. I could use this experiment to find it. But not only that, probability can work in the other way, is that rather us knowing what we've got, we can work backwards to work out what we started with. And this simulation, the coloured balls, is an example of that. Okay, here we've got a simulation showing us a problem. There are 12 balls in a box of 3 colours, red, blue and green. How many of each colour are there? Now, there's no way of knowing this. It could be 12 greens that we've got from our first trial, or it could be, they could be all equal. It could be anything. Now, what we could do is that if you took one ball out each time and recorded that, put it back in and so on, you could then work out from the probabilities with a relative frequency how many there are. And the way to do it is to do it a number of times. So if I put in 12, what you can see is we've had a go at drawing 12 balls, and what you can see is straight away there's the probability is higher for green. So based on this, it's saying that we've done it 12 times, we've got 2 reds, 8 blues, and we've ended up with a total of 12. That gives a relative frequency there, meaning that our expected number is 2, 2, and 8 of that. Now, if I increase that to, say, 120, what we end up with is something slightly different. So after 120 trials, we've got 12 red, 9 blue, 99 green. Now, if we look at the expected number for that, of our 12 in the box, there's 1.2, 0.9, and 99. So if I had to guess this time, I would say that there is 1 red, 1 blue, and 10 green. But again, the number of trials doesn't tell us the full story. So if I did it 1,000 times, okay, so it's changed again. So we've ended up with expected numbers of 0.9, 2.172, and 8.9. So again, that would suggest that it's 1, 2, 9. But what we should notice as we increase, our numbers, that the variation should be less variable. So we've got 1, so we could round that to 1, 2, and 9 again. So that's looking probable. If I change it to 2400, you can see again it's now settled on that 1, 2, and 9. 3,000. So if I did the 3,000 trials of just simply taking a ball out of the box and putting it back in, we end up with these numbers. And if I'm rounding, because we can't have part of a ball, that it must be 1 red, 2 blues, and 9 greens. So you can see by simply using relative frequencies and expected numbers, we've been able to work out something without actually knowing what there is inside the box. And this is what we do with things like that we have no idea what the probability is or the outcome is. So this is really important. So an example that we've got is looking at ACC claims. So there's no way of us predicting how many ACC accidents there's going to be. But what we can do is look at some of the accidents that people have claimed for. So what is the probability that you are going to be injured or need to make an ACC claim for agricultural, forestry, or fishing? Well, there was one out of per 1,000, there's 190. So the probability of that, of agriculture, fishing, and forestry, is equal to 190 out of 1,000, which is equal to 0.19. All right, and we can compare that to something like mining. And mining is 97, which is equal to 97 over 1,000, which is equal to 1.097. So straight away we can see that you're twice as likely to be injured from agriculture, forestry, or fishing than mining, which is rather surprising how dangerous that is. Luckily for me, teaching's way down there, which is about a quarter of what the probability is for forestry and fishing. So the key thing is experimental probability is all about this equation here. Finding the number of times an event occurs and dividing by the number of trials. So there's a link in your OneNote lesson from the workbook. So if you could make a start on that.